This is an introduction to the other main huge topic of our course, which we're finally getting to, which goes under the name of integration, but we're going to introduce it in a couple of ways. One is a fairly natural problem, that's finding an area of a certain region in the plane. And we know how to find areas of rectangles and triangles and trapezoids, things with straight lines basically. But what if we have the area under a curve? And so, for example, suppose I have y equals 1 plus x squared. That's a parabola. It would start out here and then go up. If x is 1, y is 2. If x is 3, y is 10. And I'm going to look for the area under this curve between x equals 1 and x equals 3. And this is going to be the prototype for the kinds of areas we can calculate. And we're going to be able to do more than this. We're even going to be able to do some volumes a little bit, 3 dimensions. But the area under a curve from some certain x to another x, and this is usually often called A. This is called B. So the area from A to B under the curve y equals f of x. So let's say that's our function. And that's actually rather tricky. It's not obvious even how to define it, and if you actually think like a mathematician and are really skeptical, it's not even clear that it is well defined. And so what we're going to do is we're going to not try to attack it directly, we're going to try to approximate it, and that should sound familiar because that's what we did with derivatives. The slope of the tangent line seemed at first like a reasonable thing, but then when you start thinking about it a little bit more, it's rather tricky, and the way we approach that is through an approximation procedure and taking limits. And we're going to do the same thing here. And what we're going to start with is to realize the simplest thing we know, the only thing we really know well how to take the area of is a rectangle. We do know triangles and trapezoids and things, but if you actually think back to how we derived those all came from rectangle formulas. So what I'm going to do is something very explicit. I'm just going to divide this up into divide the interval up into a few regions, a few subintervals, and I'm going to divide it up into 4. So here's 2, 1.5, 2.5. And I'm just going to draw a rectangle, and I'm going to try and make the rectangle pretty close to the same height as the graph. Now, there's a few strategies for that, and we'll discuss the different strategies. But the first one I'm going to talk about is called the left endpoint method, where I just take this little interval, I evaluate the function at the left endpoint, and I make a rectangle of that height. And I'm just going to add up the areas of these rectangles. That is not, obviously, going to be exactly the right area, but it's a start. And also, as I just mentioned, there's other choices. I could have chosen the right endpoint. I could have gone up for this first rectangle. I could have made it match at the right corner and gotten something that was like this. But just to start out, I'm going to use this left endpoint method. Okay, so let's do that. So I'm going to get 4 rectangles. And let me introduce some notation. Here, n, the n is going to be our number of rectangles, and that's 4. And that's going to be our usual notation for how many rectangles I use, and that's going to be a crucial number. And I'm going to introduce a really handy notation, delta x. We've seen that notation before. That's supposed to be a small change in x. That's going to be b minus a over n. In this case, it's 3 minus 1 over 4 is 1/2. It's equal to the width of each rectangle. If you get more sophisticated about this, you can use different widths for the different rectangles, but we're always going to use the same width for each rectangle. Almost always. It's going to be simpler that way. And so you might be thinking, wait a minute, I thought delta x was supposed to be a small change in x. 1/2 isn't that small a number. And that might give you a clue as to the next stage here. We're going to make n bigger, delta x smaller, and we're going to get a finer and finer mesh here, and we're actually going to get a better and better approximation. And only in the limit are we going to actually get the right answer. But that's going to be something that is a little later on. Let me change colors because the black is kind of fading out. Okay, so the area of the first rectangle, let's call it A1, is just height times width. The width is easy. That's the delta x. And the height, how did I choose the height of the rectangle? I chose it by looking at an f value. And so that's f of a, so explicitly f of 1 in this case, and then times the 1/2. And f of 1 we know is 2. So that's that first rectangle. That's rectangle number 1, 2, 3, 4. Area of the second rectangle is again height times width. Really basic. Now that's going to be f of 1.5, but I want to show you the pattern here. It's a plus delta x. You start at a, you skip over one delta x unit, and you're on the left endpoint of the second one. And so that's going to be f of 1.5 times 1/2. So I need to put 1.5 into my formula. So that's 1 plus 2.25 times 1/2. And that's, let's see, that's 9/4, 13/4 is 13/8. And let me say right off the bat something that people always get mixed up with here is people get lost in the kind of bookkeeping and forget the most essential thing of the whole thing. They don't evaluate the function f. This is height times width. 1.5 just tells you where to build your rectangle, where to go up to meet the curve. You got to go up and actually meet the curve to get the right rectangle. A lot of people the f just disappears, and it's the most important part of the whole problem. It's a shame. Okay, A3, area of the third rectangle, again height times width. F of, let's see, what are we doing? We're starting at A, and we're moving over 2 delta x's to get to that left endpoint of the third rectangle. Again, times the width of delta x. Now that happens to be 2. And so 1 plus 2 squared is 5. So that's 5/2. A4, continuing the pattern, that's, we go from A, skip 1, 2, 3 units of delta x to get to the left endpoint of the last rectangle. And that's f of 2.5. Let me do it all as fractions from the start, unlike the way I did 1.5. Okay, so that's 1 plus 25/4 times 1/2. So that's 29/8. So the total, A1 plus A2 plus A3 plus A4 is equal to 1 plus 13/8 plus 5/2 plus 29/8. Let's put it all over 8. 8 plus 13 plus 20 plus 29 over 8. Notice these numbers are getting bigger. That makes sense because the rectangles were clearly getting bigger as we went over. So that's 21. This looks like 70 over 8. And there's an approximate version of this area. That's just approximate. It's definitely missing these little segments in here, these little sort of curvy-sided triangles in here. But the next step in the story is going to be, well, what would happen if I took n equals 10? It'd be more work, although for a calculator or computer it's not really much more work. And we should get a better approximation. Because if I took n equals 10, with that same curve, and I took these rectangles, if I took smaller rectangles with smaller bases, what you notice is that there's less stuff missing. Compared to the big chunky stuff I'm missing here, there's less and less that I'm missing in here. And that's the way the story is going to go. We're going to take, in the very near future, we're going to look at first what happens if I take larger and larger n, and so delta x is going to go to 0. And then we're really going to take the limit. So the limit as n goes to infinity, and the limit as delta x goes to 0. That's going to become a pretty involved procedure, something that we do have to do in real life a lot, although we often use computers to do it. But then we're going to see that in a lot of cases we get a good shortcut called the fundamental theorem of calculus.